Kia ora and welcome to this video on question 1 of the 2018 Skull Calc exam. The question is all trig related. Okay, every question is geometric and has trig identities and whatnot in it. Usually question 1 is the more reasonable of skull papers. However, this year it was actually one of the trickier ones. So I guess it always pays to look at the paper as a whole before you just jump into a question. This question here starts off with a proof, which isn't necessarily the easiest starter. I'm going to show you two methods to solving this problem. First principles generally means, like in this context, if we want to prove a formula that's on the formula sheet, we need to use other geometry that we've learnt in earlier years to prove it. So if we've got cosine of a minus b, and that's the thing we're trying to prove, we can use the cosine rule. So we look at this triangle here. This angle here is alpha minus beta. And there's a rule that relates angles and sides together. Okay, so I'm using that from 12 calc. I guess you could argue maybe I have to prove that too, if I want to prove the whole thing using first principles, but we could be there a while and we might end up having to prove that 1 plus 1 equals 2. So let's just use it without proof. So we've got a 1 on either side of there because it's a unit circle. And then we've got some length QP. QP is the distance between those 2 points. Well, Q has the coordinates of cos beta, sine beta. And P has the coordinates of cos alpha, sine alpha. Okay, so the x value is always the cosine of the angle, and the y value is always sine of the angle. And that's why when your angle goes above 90 degrees, your x value becomes negative. Your sine value changes sign after 180 degrees. So the unit circle and trig graphs are related, and hopefully you have a good understanding of that. Okay, so using the cosine rule, we've got c squared, it's a squared plus b squared minus 2ab cos c. If you've never seen this before, it's on the formula sheet, but it's covered in level 2 trigonometry. So the lowercase letters are the sides and the capital letters are the angles. We've only got one angle in this problem. So c squared, which is qp squared, a and b are the sides 1 and 1, so 1 squared plus 1 squared minus 2 times 1 cos with alpha minus beta. The only thing you need to know with this notation is that little c will be opposite capital C, the angle. The angles A and B will be opposite the sides A and B. Okay. Now QP squared is the distance between those 2 points. So we can use Pythagoras on that. We'll make a right angle triangle like that. Hypotenuse squared will be equal to the sum of the squares of the other 2 sides. So for that we need to find the difference between the y values and square, the difference between the x values and square. So we've got sine beta minus sine alpha all squared plus cos beta minus cos alpha all squared. That's the QP squared equals 1 squared plus 1 squared, so 2 minus 2 cos alpha minus beta. Okay, and then we expand out sine squared beta minus 2 sine beta sine alpha plus sine squared alpha plus cos squared beta minus 2 cos beta cos alpha plus cos squared alpha. That's the left hand side, equals 2 minus 2 cos alpha minus beta. Now, yeah, I'm not so happy about this problem because the way I've done it here, first principles, is not really holding, because I now need to use a trig identity to explain why that's 1, and this one here is also 1. Sine squared plus cos squared always equals 1. So those green things actually both equal to 2. So it's not really first principles. And then I can divide everything through by minus 2. And then you've got your proof. When you prove something, put a box at the end of it. I like to put a box with a smiley face. So yeah, I've used a couple of rules in there that I guess in a calc class you would learn those before the rule we just proved. So I guess the rule we proved develops from other things. I don't particularly like it. First principles, I should have used some right angle trig in there. And anyways, I did say I was going to look at it from a couple of different ways. So feel free to skip to the next part if you're not interested in this second method. Method 2, I actually stole this from one of my students who did this exam, and they talked about complex numbers. So if you've studied complex numbers at scholarship level, you might have seen this relationship here: e to the I theta is cos theta plus I sine theta, which we know in NCA maths to be cis theta. E to the I theta is another way of writing that. It's called Euler's form, polar form. And so if we make the theta alpha minus beta, or should I make it alpha minus beta? Let's think about this for a sec. Let's see, e to the I alpha minus beta equals cos of alpha minus beta plus I sine of alpha minus beta. So this complex number here has got a real part and it's got an imaginary part. In the left hand side, we can write it using power rules as e to the I alpha times e to the I minus beta, or even better, e to the I alpha over e to the I beta. Okay, so that's the left hand side becomes two complex numbers that are divided, and that when you divide complex numbers in polar form, you subtract the angles and you divide the modulus. The modulus in this case is 1 for both of them. There's no number in front of the e, but the angles subtract. So we would end up getting e to the I alpha minus beta, which is what I had. Okay, so that holds. Now, e to the I alpha is equal to cos alpha plus I sine alpha, and we're dividing by cos beta plus I sine beta. And when you divide complex numbers, you would have known, or you would have learnt about how to times by the conjugate. So cos beta minus I sine beta over cos beta minus I sine beta. And the denominator of this expression turns out being cos squared beta plus sine squared beta. The numerator, which equals 1 by the way, the denominator, the numerator becomes cos alpha cos beta plus sine alpha sine beta. The other real terms, the real terms come from taking this and timesing by that, and also the imaginary term timesing by that, and the I squared makes -1. And the other terms are both imaginary, so we get plus I times sine alpha cos beta minus cos alpha sine beta. And like I said right at the start, we have a complex number, e to the I alpha minus beta, which has a real part and an imaginary part. Now if I take the real part of that and look at the real part of this, if I equate the real parts, I've got my proof. Therefore, cos alpha minus beta is equal to cos alpha cos beta plus sine alpha sine beta. And I can actually prove the other one too, because if I equate the imaginary part with the imaginary part there, remembering that the denominator equals 1, then I get the compound rule for sine. Pretty neat. Okay, the second question, part B, is an optimization problem. Where should P be located in relation to A so that the angle APO is a maximum? Justify your answer. So if you think about this, you might think about putting P directly at the top of the on top of P. P on top of O, and making a triangle like that. And what happens when you do that is you make the height the biggest, and therefore you actually maximize the area. You don't maximize the angle. Turns out that the answer is to put P either there, directly above A, because that will maximize this angle, or directly below it. But we've got to prove that. I'm going to show you quickly before we get into a diagram that might help you understand it. If you've never used GeoGebra before, it's a great little app. First thing is we've got a circle. The question says, consider a circle. So let's just put the circle anywhere. Doesn't really matter. Turn the axes off so that we don't get confused. Alrighty, the center of the circle was called O in the problem, so we'll rename it as O again so that we don't get confused. And then we've got another point that's inside the circle, which we're going to call A. And then that point B, we're going to rename it as P. Okay, we're good to go. Now, one thing that the question didn't state, it kind of looked like OA had to be on some sort of horizontal line with each other, but it doesn't really matter because you could rotate the thing. A can be anywhere inside the circle, so let's say it's there. Now, at the moment, if I move P, my circle's moving, which I don't really want that to do. How am I going to fix this? Okay, sorry team, I'm just going to delete this point. Get rid of my circle. I'm going to make my circle have a fixed radius, so I don't want it moving around. Number expected, yes. I don't know. 10. Oh, far too big. How about 1? Too small. Sorry team, using an iPad, it's not particularly good compared to the MacBook. Give me that circle. Alrighty, we're good to go now. Point on the object, that point B, like I said, we rename it, make it equal to capital P. Should have prepared this earlier like a good cooking show. Alrighty, A is now stuck on the circle and the circle ain't going to move. Brilliant. So the last thing is we're going to track the angle that we're trying to maximize. Not that one though. Not the acute angle. Boom, boom, boom. Okay, 30.8. Now, let's have a look at how that changes as we move it. So, it seems like the biggest is around 31.06, and it turns out that is when that equals 90 degrees. Okay, so our answer to the question, the biggest value of that angle, occurs when OA and PA are perpendicular to one another. Okay, now we just got to prove it. So, let's draw out that triangle again. I'm going to put A somewhere random, put P somewhere on the circle. I don't know that this is the right angle at the moment. Okay, what I do know is OA is a constant, so we'll call it K. It's A is not moving, it's a fixed point inside the circle, and we know that OP is just the radius of the circle, so that's also a constant. And we want to maximize this angle up here, which I'm going to call theta. And there's another formula, like, you know, we used the cosine rule in that last question. There's a sine rule from level 2 trigonometry as well. That is A over sine A equals B over sine B. So if I apply that to this triangle, I get K over sine theta, because K is the side opposite the angle theta, so K over sine theta is equal to R over sine of alpha, where the angle there is alpha. Okay, remember my objective is to maximize theta. So if I rearrange this equation, I'm going to have sine theta by cross multiplication is K over R sine alpha. Now, alpha's free to vary, because if P moves, alpha changes, and so does theta. But what I do know is that this thing here has a maximum value of 1. Sine alpha is never bigger than 1. And so therefore, if I want to maximize theta, that's my goal. I don't need differentiation for this, but to maximize theta, I need to maximize K over R sine alpha. And therefore, alpha is equal to pi over 2. Okay, because sine of pi over 2 is 1. That's the biggest value that the right-hand side will be. And that biggest value will give the biggest value of theta, because it gives the biggest value of sine theta. If you think about the sine graph, theta, sine of theta, as theta increases up to pi over 2, it keeps getting bigger and bigger and bigger. If I want the biggest value of it, now theta can't be pi over 2. Okay, you can look at the diagram there, theta can't be pi over 2. But it's going to be somewhere, you know, in between 0 and pi over 2. And as it increases, so does the value of sine theta. The biggest value of sine theta will exist when alpha is pi over 2. Okay, so it's a nice little proof there without using differentiation. Okay, the third part. Every few years they give you a beast of a trig identity in scholarship. If you haven't solved basic trig identities, and this is probably not one where you learn the art, but by all means follow through and see if you can make sense of it. With this question, I'm going to start on the left hand side and play around with it, and then I want to come out at the end with the right hand side. I'm starting on the left because generally with a trig identity you start on the side that you can algebraically simplify first. So I look at that left hand side and I go, okay, put the fractions together, I can make some progress. Okay, so left hand side equals, let's put the fractions together. Okay, so that's what we've got so far. Now, I only expand stuff if I really feel I need to. The denominator I'm aiming for has 3 terms. If I expand this, I'm going to get 4 terms. So I'm going to get an extra term I don't want. So I'm going to leave it factored. In the numerator, I'm looking for cosine theta minus sine theta. I don't have that, but if I expand this numerator out, there's a cosine theta minus sine theta. Now there is a formula on the formula sheet that turns cos squared theta minus sine squared theta into the double angle formula. Okay, if you look on the formula sheet in front of you, there's cosine squared theta minus sine squared theta is cos 2 theta. I don't want to use that because that will bring in double angles, 2 thetas, and the right hand side I'm aiming for doesn't have any 2 thetas, so I'll be going away from the answer if I do that. Okay, so always keep an eye on the right hand side and where you're heading, because you might go past the answer. Okay, so I'm not gonna, why is it not erasing? Oh, it's gonna have to stay green, sorry team. Okay, so I'm not going to, I'll try erase it one more time. Oh, there it goes. Having a bit of laggy behavior going on here. So what I'm going to do is factor these. Well, I don't need to factor that one, it's just cos theta minus sine theta. Probably helps if I write in the denominator again. Cos theta minus sine theta plus, so that's one of the terms put together. The other one's cos squared minus sine squared, which is a difference of 2 squares. That's what I want to do. Algebraically simplify. A squared minus b squared, a minus b, a plus b. So I've got cos squared minus sine squared is cos theta plus sine theta, cos theta minus sine theta. Okay, there's a common factor. The numerator now has a common factor. Oopsies, it's not that one though. It's that one. So I can factor that out. Multiplied by 1 plus cos theta plus sine theta. Now this is where, if you know where you're heading, you would be freaking out right now, because the denominator that we're trying to achieve has appeared in the numerator. Let's go back and look at the question. 1 plus sine plus cos has appeared, 1 plus cos plus sine, in the wrong place. Okay, so when this happens, this is how you fudge an answer. You put it in the denominator where you want it. It turns out we're not actually wrong. But if I put it in the denominator where I want it, I need to put another one in the numerator. Okay, and like I said to you earlier, I only expand where I think it's necessary. Well, let's look, what have we got? We've got this part which we want. We've got this part that we want. Okay, let's go back, look at the problem again. Got that bit. So the only thing we haven't got is a bloomin' 2. How the heck do we get the 2? Well, the rest must equal 2. So that's now where I start expanding. Okay, so I don't play with any of the other stuff because I'll go past the answer. Multiplied by, it's going to be good fun, but I expand. Okay, 1 times 1, 1 times cos, 1 times sine, etc. 1 times 1, 1 plus cos plus sine. and then cos times all of them, cos squared, cos sine. This is where c's and s's would help quite nicely. If you said let c equal cos theta and s equals sine theta. Okay, then the last term, sine times every one of the brackets, sine cos. Can you run out of book space, although I'm off the screen, it's fine if you're on a device. Then the denominator fortunately is just a binomial, so two things multiplied together. So 1 plus sine plus cos sine. And apparently this equals 2. Okay, this is where it's really neat. Sine theta, there's 2 of them. Cos theta, there's 2 of them. 1, there's 2 of them. 1 there, and a cos squared and a sine squared. That makes another 1. And then the last one, cos theta, sine theta, cos theta, sine theta, 2 of them. So the numerator is just double the denominator. So we can write cos theta minus sine theta that probably needs a bit of explanation in your answer booklet. Something like numerator equals 2 times denominator. Maybe even explaining why the cosine squared plus sine squared, what we did with that. And then therefore that equals the right hand side, close bracket, close box, smiley face, happy days. That's question 1 of the exam. See you in later videos.